In this first practice problem, we're given a three-phase system. I will assume, I don't have any information to verify this, but I'll assume it's a delta connection, and it's a 230 volt kV, 230 kilovolts line to line, and it's delivering 200 megavolt amperes to a balanced load with a 0.9 power factor lag. So this load is being delivered 200 megavolt amperes, 0.9 lag power factor. The first part of the question is to find a line current that's flowing in this circuit. Well, in order to do that, we have to start off by solving for the current in each one of these phases. And the current in a phase would be obtained by taking the total megavolt amperes, that's 200 times 10 to the 6 volt amperes, and we will divide this by 3 because there are 3 phases, and then I will divide that by the voltage across each one of these loads, which is 230 times 10 to the third, and this gives me a current of 289.9 amps. But now that's the phase current. That's current flowing in one of these phases. We'd like to find the current flowing in the line. Well, the current in the line is equal to square root of 3 times the current in a phase. So we have square root of 3 times 289.9, and that is equal to 502 amps. In the next part of the problem, we'd like to do a power factor correction. And if we consider just one phase only, we know that the current flowing in any one phase, as we just saw a little while ago, was 289.9 amps. But now since the power factor is 0.9 lagging, that tells me that this load is resistive and inductive both. So there's a component of this current that is flowing through the resistance, and there's a part that I will call as the resistive component, and there's a component that's actually the inductive component. So what I'm really trying to put together here is a triangle that looks like this, where I have the component of current that's flowing through the inductive reactance. This is the current through the resistive part, and this is the total current, I phase. So this is 289.9, and I know that this angle theta is an angle whose cosine is equal to 0.9, then I can solve for that angle, which I believe is 25.8 degrees. 25.8 degrees. And from it I can find these two components. And these two components respectively are, first, the component that's flowing through the inductive reactance would be equal to 126.4 amps, and the part that's in phase, the part that is real, is equal to 260.9, and these two, if you use Pythagoras' theorem, will give you 289.9 as the resultant. Well, what we'd like to do is to cancel this component out to get unity power factor. So I must add a capacitance across here in such a way that the capacitive component of current is exactly 126.4 amps. If that's to be the case, then the compensating current, the cancellation current, would be 126.4, but now I've got to use a capacitor to offset the effect of the inductance. And the 126.4 amps we know is flowing through a capacitance. No, that's the current. We want to find the capacitive reactance. We would do that by taking the voltage over the current. Well, the voltage across here, we already know, is 230 kilovolts. And the reactance, we know, is 126.4 or the current's 126.4. Hence, the reactance would be equal to 1,820 ohms.